Next presentation, José Almeida from Polytech of Porto, Portugal, with the work Illuminating Metaheuristic Performance using Vortex Map Elites for Risk-Based Energy Resource Management. José, nice to meet you.
Okay, so good afternoon to everyone. As was said, my name is José Almeida, and I'll be presenting Illuminating Metaheuristic Performance using Vortex Map Elites for risk-based energy resource management. So a big problem, this is more of the computational intelligence optimization algorithm part of sites, because it doesn't pass. Oh, sorry. Yeah. So I'll first give a small introduction to the theme, why we want to illuminate this metaheuristic performance. Then I'll present the methodology regarding the formulation to our problem that you want to optimize. And then I'll explain this algorithm, this Vortex Map Elites algorithm. Then I'll be presenting the case study where we did our resource management. And then that's a mistake there. It's not iris parameterization. That will be the next presentation, so sorry about that. And then I'll be discussing the results and give some conclusions. So when it comes to the energy sector, as we are seeing with the goals in the European Union, mainly to decarbonize the energy sector, we are noticing an increased penetration or renewable generation, mainly wind and photovoltaic, and as well as the transition from the combustion engine vehicles to electric vehicles. These sort of resources are variable and uncertain because, for example, renewable generation depends on weather conditions, for example. Electric vehicles depend on the user behavior. So this uncertainty associated with the management can jeopardize the entire operation of the energy chain. So in this case, we formulate risk-based energy resource management to create a reliable and resilient system that deals with this uncertainty. But then again, as I said, this problem is a stochastic problem. So and a very large problem. So we diverge from mathematical optimization approaches and introduce the metaheuristic optimization algorithms. But these algorithms have some sort of disadvantages. So, for example, they do not guarantee the optimality as mathematical approaches do, and they lack some sort of explainability to the user. So the user does not fully understand the solution that they are given. So in this case, we take which is called the quality diversity algorithm, mainly the multidimensional archive of phenotypic elites, which is map elites, which basically, I can come here, discretizes this high dimensional space, which is our variable space, and it discretizes it into features, into descriptors that we want to analyze for our problem. As I said, the map elite algorithms explores a high-dimensional space to identify the most optimal solution, in this case, a most optimal region, within a low-dimensional feature space. So when it comes to the formulation, we want to minimize the EI.A costs. In this case, we formulate the EI.A costs as a weighted sum of expected costs plus our risk aversion to deal with the uncertainty times a risk cost. Then, to not bore you with the formulation, this is how you calculate. The expected cost is the weighted sum of the scenario costs. We have multiple scenarios for the energy resource management. Then we also optimize the costs associated with the risks. So when it comes to the Vortex Map Elites is a simple algorithm which basically uses the variation strategies of the genetic algorithm, which is not that great, as we will see. So what we did is we improved this algorithm with what we call Vortex Map Elites. This algorithm is simple. First, we create an empty archive where we will store our solutions. Then, as we do in any metaheuristic, we create a random number of solutions, and then we add them to the archive to have an initial archive. Then, in the iterative process, what we do is we implement the vortex variation. This is a very simple algorithm. We declare a center, which in this case is our best solution from the archive, and then we create a radius to evaluate new candidate solutions, which is basically this formulation here. This is to create the radius, and this is to evaluate new candidate solutions. Then we test if it is within the boundary constraints, and then we add it to the archive where there will be competition, and the best solutions will be stored in that archive based on our feature descriptors, which in this case, we evaluated the demand response and renewable ratios. So for our case study, we use the distribution network of a mock-up smart city, which was created by one of our colleagues in JCAD. And this network has a high penetration of renewables and electric vehicles. Initially, we had 5,000 scenarios, and then we reduced it to 15 to diminish the complexity, the computational complexity. Here we can see the variation of the scenarios. We have PV generation, wind generation, the load consumption, and the wholesale electricity market prices, which were uncertain parameters. So when it comes to the results, we implemented the simple version of map-elites with the genetic algorithm variations, and then we tested the Vortex map-elites. As you can see, the Vortex map-elites improved the results in every single way. And as you can see here, because in every metaheuristic we need to test the robustness of the algorithm. So we tested for 20 runs, 20 trials, and we can see that Vortex map-elites outperformed the map-elites algorithm in every single trial. Here is also another test for robustness, which is the convergence of the algorithms. And then we can see here the archives, which is where we store our solutions. So we can see here that for map-elites, both have very poor initial archives with little diversity or on the ratios that we wanted to test. And then, for example, Vortex map-elites presented a more diverse archive with more solutions, and it presented an optimal area to the ratios that we wanted to test. So with these results, we can present to a user, for example, where our optimal area is. So it gives them some sort of trust in the algorithm. So to conclude, in this work, we proposed an improved version of the map-elites algorithm, where we implemented a very simple algorithm, which is very effective, which is called the Vortex Search. We achieved a very high archive diversity for the Vortex Search algorithm, where this Vortex Search algorithm diminished the costs where we wanted to optimize, because it created a more diverse with more solutions in the archive. So when it comes to future research, new dimensions, new features can be added that we want to analyze that could be interesting to our problem. So here we need to have some sort of knowledge about the problem that you want to analyze. And we also can integrate other variation processes based on other metaheuristic algorithms. But because, for example, we implemented Vortex, but I read some works that they implementing an algorithm based on covariance matrix that are obtaining already good results. So there's an N possibilities that we can implement with this study. This is my biography. If you want to contact me for anything, I'm a PhD student, by the way. And that is all for this presentation.
Thank you, Jose. Some question from the audience?
No.
You can just return to that map of the results.
This one?
Yeah, I would like to understand better this region that you highlight here. What's
Yeah.
this mean to this solution?
This is basically the lowest costs that we obtain for these ratios, because in the algorithm, as you wait. In the algorithm, we evaluate those candidate solutions, and then we add it to the archive. The evaluation gives us the fitness value and those descriptors, those behaviors. And then those behaviors will tell us in the archive what it is in the archive. So for example, one solution returned this behavior, 0. Blah, blah, here. And then inside this small rectangle in the archive, it will compete. For example, if the solution that was previously there was worse, then we update the new solution. If it is better, we keep the best solution there, and that's it.
The part of the genetic algorithms itself.
Yes.
Okay.
Yes.
Thank you again.